Section 8.2, sine and cosine curves. So now we're going to kind of expand a little bit of our knowledge on our generic sine and cosine curves. Last chapter we took a look at sine, cosine, tangent, and also their reciprocal function curves. But we're going to do a little more emphasis here with sine and cosine. Specifically, we're going to look at today what happens when we have a coefficient involved. Sometimes we have a coefficient out in front of our function, as in the case right here. Or sometimes we have our coefficient hanging out inside of the function, as in the case here. And in Algebra 2, you guys went over this, but whenever we have this C value, which is called our stretch factor, whenever that is on the outside in front of the function. Now when it says f of x, that means it can be any function, a cubic function, a quadratic function, a linear function. And it might look something like this, like for example on a quadratic, if we had y equal 3 times, I'm just putting the parentheses in here for just emphasis, so 3 times x squared, the function f of x is x squared, and we have the 3 hanging out in front of it as a coefficient. That's a vertical change. Now, we did a lot with vertical change. We didn't do a lot, though, with this situation where I have the C on the inside. So the vertical change, the 3 is hanging out in front. It vertically stretches the graphic. It's 3 times as big vertically. And it's actually going to be different with horizontal. So the C inside the function, and again, as an example of what that might look like, is if we use the same value, but now I put the 3 on the inside with the x squared, something like that, for example, or maybe we have 3x, and I'm going to just throw a little translation in there as well, which we'll talk about later. So in the 3 inside the function here, now we have a horizontal stretching or shrinking going on. We'll always refer to things as a stretch, even though sometimes our graph might shrink. Now, the thing is with the horizontals, you'll notice that the horizontal stretch factor is this 1 over C value. So that 3 on the inside here causes me to horizontally become a third of what it normally is in the x directions. Now we're talking about parent functions, so in our classes we use critical movement. So what would happen there is my graph, after it translates to wherever it has been translated via the x minus or plus a number, there's my left or right translation. And then if I had a number out here, that's my up or down translation. I move my starting point, which is my vertex, to those locations. And then I would have my normal parent function movements. Well, in this case right here, where I have a 3 on the inside, what would happen is my parent function movements would, in the x direction, would become a third of what they normally would be. And so that's the thing here with the stretch factor. So pay attention to the stretch factor for horizontals. It's 1 over C. Whereas verticals, it's just what you see is what you get. So 3 means 3 times as big for the y movements. And that's what we're going to do with our sine and cosine curves. They obey the same rules as the other functions. So we're going to emphasize today just this horizontal and vertical change. Now we're going to talk about them with sine and cosine because these guys are called periodic functions. They have a repeated pattern, making it periodic. We're going to introduce, we talked about it in the last section, we're going to introduce period to you, and we're going to talk about amplitude. Period is how long it takes for a function to go through what is called its cycle. And a cycle would be the pattern that repeats. And so here's some generic notation that we will use, and this can apply for sines and cosines. But the A, the amplitude stuff, is our stretch factor vertically. And then the B, things on the inside of our function, is our horizontal stretch factor. And that's going to have to deal with our period, actually. So this B value is going to be related to period. And A, the coefficient out front, is going to relate to the amplitude. So we have those relationships here. And again, we're talking about amplitude as an absolute value. So even if that was a negative 4 out there, our amplitude would still be 4, and the negative would just simply tell us we reflect over the x-axis. Now notice the relationship between the b and period. This is one of our many different equations you guys are going to have to definitely memorize. Period is related to this b value by this relationship of t equal 2 pi over b. It could also, if we're talking about degrees, it could be t equal 360 over b. That works as well. All right, so this b somehow affects my period, makes it shorter or longer. The a affects how high or low the graph is going relative to what's known as its axis, its horizontal axis. Here is another equation. We're going to keep adding onto our list here. So how do we find amplitude? If amplitude talks about the highest and the lowest points relative to some axis line, then we can say that the amplitude is the maximum value, subtract the minimum value, and then divide that by 2. Basically, you're saying what's the high point, what's the low point, and cut it in half. And that will be the amplitude of our curve. So those two new equations there, the red one and the a equal max minus min over 2, are going to be what we add to our list. So let's take a look at what do the coefficients of 2 do to a sine curve when the 2 is a vertical change versus a horizontal change. So first of all, we'll look at, here's our generic sine function going through one period. So the x-axis is in pi, or radians, and the y-axis is just our normal values there. So there's our sine curve. And we know that we break our sine curve into quarters, and that at 90 degrees, or pi over 2, I'm at 1, and at 3.14, or pi, I'm at 0, and at 3 pi over 2, I'm at negative 1, and then at 6.28, or 2 pi, I'm hanging out back there at 0 again. So those are our quarters. Now what happens if we vertically stretch this graph? So the 2 that's in this equation here, that 2 should make these points, these highs and lows, stretch by a factor of 2. And that's really all that should happen. Nothing else should change. It's just those points should be vertically now stretched. So let's see what happens. Here's our sine curve with the vertical change, and that's exactly what happened. Those points of 1 and negative 1 became 2 and negative 2. All right. And just to look at our equation for amplitude here, amplitude would equal max minus min over 2. And in that new graph, we had a maximum of 2. We had a minimum of negative 2. And we're dividing by 2, so we get a 4 over a 2. Or an amplitude of 2. And there it is. There's my amplitude of 2. All right, let's take that graph off. Cut that one. Oops. I have to disconnect. Disconnect. All right. So we're going to put the sine graph back on. The normal sine graph. Let's get rid of these. Our normal sine curve. Now what happens when this 2 is inside of the function? Remember, that's a stretch factor horizontally of a 1 over c, or a 1/2 of its normal value. So we should see all my x values become half of what they normally were. My y values are going to stay the same. So what does that look like? Well, let's look at our quarter points again. So at 90 degrees, how is it a value of 1? Which means this scale factor of 1/2 means I'm actually going to cut my 90 degrees by half and become 45. And that would mean I'm going to shift this point back to the left here and be, I don't know, right around there somewhere for 45. And my pi, or 180 degrees, scale factor of 1/2 becomes 90. So now that's going to shift back to here. And let's see what other one. We have 270, or 3 pi over 2 becomes half of that. So we're going to be back in here pi, or 360, half of that takes me back to that point. So now I should see a curve that kind of develops between these points. And then it would repeat itself if we're going to look at the cycle over a 2 pi or a 360 degree period. So let's see what happens. Oh, come on. There it is. So the red graph compared to the purple graph is your y equals sine parent function, and the red graph you see is going through all those points that we drawn up there. All my normal x movements, 90 degree, 180, 270, 360, all were cut in half because of this shrink stretch factor of 1/2. Now, you'll notice it also did something else. Let me erase the points off the curve here. And let's look at this. This is another interesting thing to consider. So notice what happened to a period of our curve. So here's a full period of the sine curve, starting, going through its cycle, ending at the same spot to start over its repeated pattern. There's one period. Well, it repeated that and went through another period out to 360 degrees. And we actually could have figured that out because we know of this equation, that our period is equal to 2 pi over b. And if our b was equal to a 2 in this case, which it was, then that means our period, which was 2 pi, now has only become pi. So that b value, the 2 on the inside, tells you how you shrink or stretch your period. It can also refer to the number of cycles you would see in the parent function graph. So it's kind of an informal look, but if I have this 2 here, that means I'm going to see 2 cycles in a 2 pi parent function period. Or 2 cycles in 360 degrees. Okay, so this is what we're going to emphasize today, is what happens here with our amplitude and our b value, which affects our period. Okay, given the following equation, we want to find the amplitude of the period, and then we're going to sketch the graph. And on here, I've already put down the parent functions. We're going to always compare things with the parent functions to see how it changes. So there's our, in purple there, we have our parent function cosine. But let's go ahead and find all of these things. So remembering in a generic formula here that your A always hangs out in front of sine or cosine. Your B is always a part of the inside part of our function. So in this case, we see that there's my A. And we're going to look at it as just, it's actually a -3 out there, but we're looking at absolute value, which makes this equal to just 3. And then here is my B value of pi over 3. All right, so identify the A and identify the B. So our A, 3. There's our amplitude. This graph is going to stretch vertically by 3. The negative, what the negative is going to do is it tells me I have a reflection. And we've already dealt with these before. Reflection over the horizontal axis, which is our x-axis in this case. Okay, so that's what the negative does. It just flips my graph over. So what I normally do, instead of moving up, I'm going to become down, or my down becomes an up for my movements. Let's develop the B a little bit further. So remember that B helps me find period through this equation, 2 pi over B. So if we find our period by putting 2 pi over 3, And then when you're dividing, we're multiplying by reciprocal here. So I get 6 is my period. Again, we're talking about radians here. So there's my new period. So I'm going to see what happens with this thing. So parent function already graphed. Let's see what this guy looks like. Bring it over. There it is. So there's a slight difference in my period. Our normal period is 6.28. This period is just 6. So they look pretty close in terms of their length period-wise. Well, you'll notice the graph flipped over. And then you'll also notice the amplitude, which, by the way, is this measurement. It's always the distance from the axis to the highest point or axis to the lowest point, is 3. There's my amplitude right there. All right, there we go. What about the next one? Now we're going to graph on the same set of axes a linear function y equals 3 and this sine function 4 sine of 1/2 x. And we're going to see how many solutions we have if we graph this thing between 0 and 2 pi. So again, on my graphs here, my axes are in radians, so you'll see that 2 pi, which is equal to 2 times 3.14, 6.28. That's 6.28 right there on my graph. Okay, so let's go find all of our respective parts. First of all, y equals 3, we can draw that one in. We're going to put that one in as a dashed line. Y equals 3 happens right there. And then what about this next one? The sine curve. Well, here's my A. My amplitude is 4. Here's my B. B is a 1/2, which means, how does it affect my period? The period is 2 pi over 1/2, which is 2 pi times 2 over 1. So I have 4 pi is my new period. So this sine curve is now going to take 4 pi to go through its full cycle, where it normally takes just 2 pi. So it stretches up by 4, which means I'm going to be maxing out up here at 4 value. I'm going to be minimum at -4 value. Let's see what happens. There it is. Bigger period, bigger amplitude. Now let's take a look at the parent function movement, since we talk about movements so much. Let's kind of emphasize the movements a little bit. So we're going to look at the parent function movements of y equals sine theta. We'll look at that table. We're going to take a look at just generic tables. Theta here instead of an x. All right, we say we graph our parent function based on some quarter points, right? So 90 degrees, I have a value of 1. 180 degrees, 0. 270 degrees, -1. 360 degrees, back at 0. Well, what happens when we take y equals sine theta and we have introduced a y equal 4 sine 1/2 theta, right? Which is the function that we're graphing right now. That we finished, that we already graphed. All right, what happens here with this table? Well, first of all, our theta y from our parent function. Remember that the a value is a stretch factor for your y's. So what happens is all of these y values multiply by 4. And we produce over here half. We talked about at the very beginning this whole concept of a stretch factor. Well, what it really means is that my thetas are getting multiplied by 2. 1 over c, or 1 over 1/2, becomes my stretch factor. So when we're talking about this stretch factor, I have 1 over 1/2, which is 2. So my y's were affected by 4, multiplying the parent function by 4. My thetas multiply the parent function by 2. And if that were the case, 90 times 2 would be 180. And 180 times 2 would be 360. 270 times 2 would be 540. And 360 times 2 would be 720. So those should be the coordinates then of this, the x, theta, and the y coordinates. Well, look at 180. There it is right there. There's 180 and 4. Check. 360. There it is right there. And 0. Yep. 540. 540 is right over here. And add a negative 4. 720. There it is right there. Value of 0. So that's how you can take the parent function table, multiply the thetas by the reciprocal of whatever b is, multiply the y's by whatever a is. And that's how we can change our graph table-wise to come up with our points. Again, thinking of always sines and cosines in terms of quarters. Look at the 90, 180, 270, 360 relationship and adjust those points accordingly and just draw for shape. And we come up with our graphs pretty quickly. All right. So what were our answers here? We're supposed to determine the number of solutions. So we look at our graph, and the number of solutions would be there and there is where I intersect. So I have 2 solutions right there. And we can go ahead and find out what those would be. So let's see. If I knew that 3 now is equal to 4 sine of 1/2 x, then we can go ahead and find our answers. So we're going to divide by 4. We're going to get 3/4 is equal to sine of 1/2 x. Now, here's where it gets a little tricky. We remember that what's under here is actually an angle. So this is like saying I have 3/4 is equal to the sine of theta. And we know that if I wanted to solve for that theta, I would do the inverse. All right, let's do that. Let's set this thing up. We have the inverse of 3/4 would actually equal this theta value here. And let's see. Inverse, we're in degrees. I believe we're in degrees. Are we in degrees? Well, we're going to go ahead and calculate it in degrees. So we're going to do the inverse sine of 3/4. I get 48.59 degrees. I know that our domain showed radians, and we're going to work with degrees here. So I would get here that theta 1 let's go ahead and go over here. We have theta 1 is equal to, what did I say? 48.59 degrees. But really, it's not theta, right? We let theta equal 1/2 x. So what we're going to go do here is we're going to, after we do one other thing, we're going to find out our other answer here in just a second. So theta 1 would equal 48.9, and we know quadrant 2 would be the other place. So we have, what, 228.59 degrees. So our two answers of just this value of this angle would be those. But we have to substitute back in what theta is. And we said theta is equal to 1/2 x. So 1/2 x equaling 48.59 degrees. We'll call this x1, means that x1 is equal to twice that, which is going to be 97.18. And then we have 1/2 of theta 2, or x2, is equal to 228.59, and that produces a value of 457.18. So because we stretched out our period, these answers are going to actually stretch out as well. So we have 90. I didn't ask us to actually find these values, but that's what we would be looking for those. All right. So we weren't actually supposed to be looking for those, but we did. So let's just see if we got in the right ballpark. So it's supposed to be, what did we say, 97 something? 97 degrees, 0.18. So is this about 97.18 right here? Right, just past my value. All right, you got a little oops here. I forgot that I'm supposed to be in quadrant 2, and so why I added, I shouldn't have added there. I should have subtracted. So I was looking a little funny. So 48.59, and that would create a 131.41 degree theta 2. Sorry about that. 131.41 degrees, and we're going to double that. This looks better. We get 262.82. Again, those would be my two angles there. 262.82. Right about there, right? We're greater than or less than our 360. Those would be my two angles that produce that intersection. So as a coordinate for these answers, we would have 90, again, in degrees, 97.18 degrees, comma 3 would be the intersection of that curve. And then also 262.82 would be the intersection of the curve. So where we have those 2 points highlighted there. All right. And now here's some for you to try. So I'll give you a couple minutes to work on them. Check in here in just a second. Okay, so we're looking at the graph now, trying to come up with the period, the amplitude, and the equation for each of these curves. This is a little more challenging. To find the equation, we need to find the amplitude and the period, so we can write our A and our B in here. So let's see what we did here for A, and then we'll peek at B in just a second. So a couple things to notice on A. We have a max and a min of -3, and there is a center line axis. We're not going to tweak this center line axis yet, but we're right on the center line at x equal or y equals 0. So I can see my amplitude, again, distance from this axis to the highest point, lowest point, looks like it's a 3. So my A is going to be a 3. I can look at the period it took to go through one cycle. So from here, right about there is this period, and we can see that it's not 2 pi. It's less than that. It looks like it's right at 4, actually. It looks as though our period is 4. Going from there to there, going through one cycle of the curve. All right, so if that's the case, if our A is supposed to be a 3 and our period is a 4, then the period again, through this equation, and we'll go ahead and do 2 pi, is how we find our B value. Period is equal to 2 pi over B. Well, we're solving for B this time. So if I rearrange this equation, I would get that b is equal to 2 pi over the period. In this case, it's 2 pi over 4, which should be pi over 2. So let's see if that b, pi over 2, shows up in my equation. There it is. There's my amplitude of 3. How did we know it was a sine curve? Well, the sine curve is the one that starts at 0, 0 and goes up from that point. So I have a sine curve that's been vertically stretched, and then it has been shrunk by this pi over 2 b value. All right, let's go peek at the other one. You guys haven't seen this one yet, so give me just a second. Freeze the video right now. Look at the graph so you can come up with the equation. Let's look at what we have. So I'm looking down here at the bottom. I see I have this negative 2 value. So once again, from this center line axis to my lowest or highest point gives me my A. And even though it's negative 2, we're talking absolute value, so I have an amplitude of 2, it looks like. Not so obvious to see. Here's the period. And it looks like, if we were to just estimate this thing, which is kind of what we're going to have to do here, it looks like we're at about, I don't know, 6.28, negative 6.28. Looks like we're right around there. So it looks like we've gone a negative 2 pi to a positive 2 pi, or in this case, a 4 pi period. Another way to tell is just from our minimum value to our back to our 0. Looks like that's 3.14. And in the cosine curve, that typically happens in a quarter of a period. So if we multiply that by 4, we're going to get the entire period of the curve. So assuming that's all good, we should have a y equal. It's a cosine curve that's flipped upside down too. Normally the cosine curve would have started up and then gone through its cycle, but this one is starting down, so it should be negative 2 cosine of 4 pi x. Forgot to convert my 4 pi. So remember, our period is 4 pi, so our b is 2 pi divided by our period. So we have 2 pi over 4 pi, which is where the 1/2 is coming from. So remember, take that period and convert it to your b value.